Okay, so in the last lecture, we discussed transmission interconnection. So, in summary, we can say that the transmission interconnection has been done in order to pool all generating stations and load centers together, and that obviously the outcome of that is whatever power we generate and deliver to the load become economical as well as reliable. Now, the next point that we have to discuss today is flow of power in AC system. Flow of power in AC system. Now, as we all know that electrical energy uh, cannot be stored in mass, means rather than batteries and that all, uh, which is very small in capacity, in which we can store the energy. But largely, whatever power we are generating, so that we have to fed according to the load which is there on that system. Means it's a live system. Means whenever there is any variation in the load, according to that, the generators has to adjust their generation so that the system frequency and the voltage has been get maintained. Obviously, simply by monitoring system frequency and system voltage, it has been judged that whatever generation and demand is there for real and reactive power, how it is, whether there is a deficit or there is a excess. And by sensing these two parameters, that is frequency and voltage, the corrective action has been taken in order to maintain it constant. In other words, in order to balance the real power generation according to the real power load and balance the reactive power generation according to the reactive power load. So that is, we already discussed in power system 3 that automatic generation control. So how the system frequency can be sensed by the speed governor, and according to that, how that hydraulic uh, mechanism has been operated through a linkage mechanism in order to open or close the wall which is feeding steam to your steam turbine. So here in AC power system, whatever load is there at all load centers of that given power system, according to that, the generation has to be go, and according to that generation and load at different locations, and the interconnection of transmission line to that loads and generators are going to decide the power flows through the AC transmission lines of that network, means all lines of that network. Obviously, as I said, the interconnection of transmission line means how they are connected, means each line is connected to between which bus, what are the parameters of that transmission line, and so on, is going to describe that power flow through that line. So, in other word, we can say that the power flow in a AC transmission lines is uncontrollable. Means we can't, if suppose we come to know that for a given loading condition and generation going on, particular line is overload. So there is no control to divert the power which is flowing through that overloaded transmission line. Similarly, if there is a transmission line which is under load, so if we want to load that line more, so there is no control in our hand to increase the loading of that particular transmission line. So that all is happen in an uncontrolled manner, and that is decided by, as I said, the location of generating station, location of load centers, and the transmission line interconnections and their parameters and so on. So in order to understand this, here some examples has been given. As we all know that the power flow through the AC transmission line, that is power flow through a particular transmission line, is given by its, suppose we can call it as a sending end voltage of that line, receiving end voltage magnitude of that line, divided by the reactance of that transmission line into sine of angle delta, where that delta is the angle difference between sending end voltage and the receiving end voltage. Now, from this equation, if we want to control the power flow through a particular transmission line, then that can be controlled either by controlling the end voltage of that transmission line in magnitude, or by controlling the phase angle of that end voltages, or by controlling the transmission line reactors. Now here, to understand this clearly, we consider that the transmission lines are parallel transmission lines and mesh transmission lines. So first we understand it with the parallel transmission line. Let's say there is a one reason, let's say there is a one reason, or we can say for an example, one utility like Tata Power having their generation in their region, total generation in their region and total demand in their region. Similarly, there is one another utility we can say, that is, let's say for an example, BEST, which is having their independent, we can say different generating stations and loads at different. Obviously, it is again, if we go in detail, then we found that it is of a one power system having some buses, and there is an interconnection of transmission line in that buses, as well as at some buses there is a generator, some buses there is a loads and so on. But here, if these two utilities are interconnected together through a two parallel transmission line, through a two parallel transmission line. Now, as I said, the AC power system is a live system. Means whatever load is there, according to that generation has to goes on, and according to that the system voltage and frequency has to be get maintained. Now, when we talk about this reason, so there is a generation and demand, and according to generation and demand in this region, there is an exchange of power among these two regions. Means if one generation is having surplus generation, one region is having surplus generation, and another region is having surplus demand, we can say, or demand is greater than the generation. So in that case, that region will draw the power from that another region, and obviously that power we can say, let's say for an example, P. P is the power which is get exchanged between this region and this region. Now the question is, how? Please try to understand. This P is decided by what? What is the load here and what is the generation is here? What is the load here and what is the generation is here? According to that, the P will flow through the transmission line. And according to that P flow through the transmission line, there will be an establishment of voltage at this bus bar. According to that flow of power, there is a establishment of voltage at this bus bar as well as at this bus bar. And from this equation, if we see both the transmission lines, their ends are connected to common buses. As their ends are connected to common buses, means what? For line 1, the end bus voltage just Vs and Vr is same as that of for line 2 also. As well as the angle delta, that is angle of Vs and Vr, that is difference of Vs angle and Vr angle, that is delta 1 minus delta 2. That is also same for both the transmission line. Means this is constant. Vs, Vr and sin delta 1 is constant for both the transmission line. Means in other words, we can say that whatever P1 is there for line 1 is proportional to the reactance of that line. We can say X1. And the power flow through the line 2 is proportional to the reactance of that line. And that proportionality constant is same for both the transmission line, because Vs, Vr and sin delta is common in both the lines. Means what? Whatever P power will be get exchanged between this bus, this region and this region, that is how get distributed through this two transmission line. This is, we can call it as a P1, and this is, we can call it as a P2, where P is equal to P1 plus P2. So P flowing through the line is decided by the operation of that regions, and how that P gets shared among two lines as P1 and P2, it is decided by the reactances of that line. So as per this equation, if we use these two equations of proportionality for P1 and P2, from that if we draw the ratio of P1 by P2, we come to know it is equal to x2 by x1. It is come to know that x2 by x1. That is, if suppose here in this example, this line 1 reactance is considered as x and line 2 reactance is considered as 2x. So according to that, x2 is 2x and x1 is x. So this x will be get cancelled. So we can easily say that P1 is 2 times of P2. P1 is 2 times of P2. Means whatever power will flow through the P1 will be 2 times of P2. Obviously, how much will be that value of P1 and P2? It is decided by how much power get exchanged between these two regions, that is P. So here we know the equation P is equal to P1 plus P2, and we know the equation P1 is equal to 2P2. So here in this equation, if we replace this P1 by 2P2, in this equation, if we replace this P1 by P2, we will come to know that P is equal to P1 is 2P2, P1 is 2P2 plus P2. That is, we come to know that P2 is equal to P divided by 3. P2 is equal to, this is P is equal to 3P2. So P2 is equal to P divided by 3. And as P2 is equal to P divided by 3, if we use this equation of P1 is equal to 2P2, or simply using P1 plus P2 is P, so using that equation, we can say that P is equal to P2 we know P by 3, so P is equal to, using this equation, P is equal to, we can keep P1 as it is because I want to find out the P1, plus P2 I will write as P by 3. P2 I will write as P by. So if we solve this, we will get P1 is equal to 2P by 3. 2P by 3. So here, whatever power exchange will be there between this region and this region, that is P, and that shared among these two transmission line will be like P1 will be 2/3 of that P and P2 will be 1/3 of that P. That is because of one line is having reactance X and another line is having reactance 2X. So in parallel transmission line, we can say that the power flow through them is decided by how much deficit is there at the receiving end or at the generating end, and how much excess surplus is there at one end. That is going to decide how much P has to flow through the lines. And sharing of that among two transmission lines is decided by their reactances. That is what we understand from this example. Obviously, as this deficit between this region and this region change, according to that value of P change, according to that P1 and P2 change. But obviously the ratio of that P1 and P2 is always, that is, P1 is always 2/3 of that P and P2 is always 1/3 of that P. That is because of line 1 is having reactance X and line 2 is having reactance 2. Practically, that values will be different. And according to that different values, that flows, that is sharing, get decided. So here, in short, if suppose the excess is, deficit is suppose goes on increasing in this region and accordingly surplus has to increase in this region. So according to that, the P flow through these two lines suppose increases. For a particular loading condition or for a particular value of P, it may happen that out of these two transmission lines, one line will be reached to their thermal power handling capacity. One line may reach to their thermal power handling capacity, whereas another line is having margin to reach to its thermal power handling capacity.
Now what happens as one line is get loaded to its capacity, so further deficit in the one region cannot be get managed through this network, because if it is further increase the deficit, so that further increase in the power has to flow through the line, and that will create that one line will be get overloaded, and because of that, that network fail will be takes place. Obviously, it's again how much is the we can say temporary overloading rating of that lines and that. So according to that, whether it may be possible to carry it for an hour or half an hour. But if it is because of we can say increased load always in a region, so obviously upgradation of that line which is getting overloaded has to be need to done. Then and then that further operation of the exchange of power will be possible. It is not possible here that uh, whatever rated capacity is there of that line, up to that we can load both the line. It is not possible, means because it is uncontrollable. That sharing is decided by the reactor. So if you want to do anything to reduce the power flow through one line which is going to overload and divert it through the another line, if you want to do that, then the solution is only to modify the parameters of the line. Solution is only to modify the parameters of the line. So here you see example 3. Here you see the example 3. In this case, what they did, here from this one we come to know that P1 is 2/3 times of P, and P2 is 1/3 of P only. So obviously this line is suppose getting overloaded. So what they did, the line which is having an higher reactance, so some of that reactance is compensated by mean of capacitor connected in series with that line. Now by connecting the capacitor in series with that transmission line, what happened? Its net reactance offered by this line is reduced, that is x minus 2x minus whatever xc is there of this. Suppose this is of reactance xc. Again, it is variable, it is controllable. If we say if it is controllable, so we can vary this xc as we require. So under these circumstances, for second line, whatever proportionality was there by 1 by x1, but for P2, whatever proportionality is there 1 by x2, that will turn out to be now 1 by 2x minus xc. Means this relation that x2 is 2x minus xc divided by x will be now the ratio of power sharing among P1 and P2. So in short, by connecting a capacitor in series with the transmission line having a higher reactance, inductive reactance, it is possible for us to divert the power from this transmission line to this transmission line. Because of change of that impedance, whatever power P is available here at this bus to flow to this end through this line, sharing we can change by controlling this XC. And obviously this XC we can control such that this line overloading can be avoided. And loading of this line we can increase, and obviously that is possible till the thermal rating of this line. But what flexibility we got here? We got the flexibility of controlling the power flow through this parallel transmission line. We got the flexibility of controlling the power flow through these two parallel transmission lines according to their thermal rating. We can manage the flows. Because of this static series connected capacitor, obviously, which is of variable sort. Again, what technical difficulties are there for designing or manufacturing the variable capacitor? So that is another we can say aspect. Similarly, one can say rather than XC, that transmission line which is going to be underloaded, means having a higher reactance, for that line we can use a phase angle regulator. That is the delta difference between this end and this end, that is what delta is there, which is delta 1 minus delta 2. Now because of this phase angle regulator, it can be for second line, I am talking about. For first line, obviously it is delta only. That is equal to delta 1 minus delta 2. because there is no any phase angle regulator in series with that transmission. But for second line, it is equal to delta 1 minus delta 2, delta 2 plus whatever addition in the phase angle we are doing here. Why I said plus? Because if you see the power angle curve, suppose this line was get operated at here. Now what I am doing, I am increasing the power flow through this line for the same. I am operating this at higher value of delta rather than this delta. Earlier it was operated at this delta. Now I am operating it at higher value of delta. That second line I am operating at higher delta. Obviously, in that case we need to say specifically for line 1. तो इसको थोड़ा हमको स्पेसिफाई करना पड़ेगा. EL1 we can call it EL1. This we can call delta EL2. That is line 2. So using this phase angle, what I did, I will increase the phase angle difference across this second transmission line. Whereas phase angle difference across line 1 I kept as it is. And by increasing the phase angle difference across this second line, whatever capacity is remained to its thermal rating, that we can utilize by controlling this phase angle. So hope you are understanding what I am saying here. So using this phase angle regulator and static series capacitor, it is possible for us to regulate the power flow through the transmission line. So that is why it is called as flexible AC transmission system. One solution is there. Rather than this phase angle regulator installing here, phase angle regulator यहाँ पे install करने की जगह, we will install on this line. And rather than doing plus, so in that case it won't be there. For line 2, it won't be there. It will be like this. And here rather than plus, we can make it minus 5 using this phase angle regulator. So what I am doing, I am reducing the phase angle difference across this first transmission line which is getting overloaded. But let's say it is operated at this point, and reducing this phase angle difference, I am reducing the power flow through it. To its thermal rating. And obviously remaining automatically will be get diverted through this transmission. So rather than X reactance, we are controlling with the phase. Same case is there. Rather than adding up capacitor here, I will add up some more reactor here in this line so that I can divert that power through this transmission. So that is also the possible solution. For this given system. So this is how the FAC devices can be used in order to regulate the power flow through a particular transmission line. Or that FAC device, as I said, may be a static like capacitor or inductor or some voltage source or phase angle regulator. Here in the second, they gave the example of how the AC transmission line operated in parallel with the HVDC transmission line having control over the flow of power. This is showing the example of how the power flow through the AC transmission line can be controlled if it is paralleled by the HVDC transmission line. So as we all know, the power flow through the HVDC transmission line is controllable to the desired value what we want to operate. How it can be controlled? Can anyone tell me how the power flow through the HVDC transmission line is controllable? How we can control it to the desired value, what we want to operate it? Can anybody tell me?
Controlling the firing angle of thyristors.
Yeah, means by controlling the ignition delay angle of the rectifier or extinction advance angle of the inverter, it is possible for us to fix the power flow through the HVDC transmission. Now, as it is possible to control the power flow through the transmission line, so whatever total P is there, which is get exchanged from this region to this region, out of that, how much we want to pass through the HVDC line, that is possible. So automatically the remaining will be flow through the AC transmission line. Means what? In other words, we can say that the power flow through the AC transmission line is also controllable by controlling the power flow through this DC transmission line by means of delta and gamma. Are you understanding what I am saying here? So whatever P has to be exchanged from region 1 to region 2, how that P gets shared among these two transmission lines, that is possible. Either we have to go with the parallel HVDC transmission line or FATS controller or any one of the transmission line in order to get the control over the sharing of power, among that two transmission lines. Please try to understand. Here we don't have the control over the flow of power from this region to this region. Control over the flow of the power from this region to this region is decided by the operation of this region and operation of this region. And according to that, whatever power will be get flow from this region to this region, how it is get shared, that is controllable. Please try to understand. It is a synchronous intertie. Means these two regions are connected synchronously, because what happened, even though one of the transmission line HVDC, but it is parallel by the AC transmission line. Yeah, if suppose these two regions are only interconnected by these two by this HVDC transmission line, not by AC, एक ही सिंगल HVDC transmission line अगर दोनों region के साथ interconnect करेगा, then that is we call it as a asynchronous intertie. Means the power flow from one region to another region is controllable in that case. But in whatever example given us, in that case, the power flow from region 1 and region 2 is uncontrollable. Are you understanding what I am saying here, Chirag?
Yes, sir.
Because it is a synchronous intertie. One of the line is AC line. So it is synchronous intertie. मतलब क्या? कि whenever AC interconnection is exist, it acting like a one system. It is acting like a one system, and because of that, whatever will be the frequency in this region, the same frequency will be there in this region. Means whatever variation in the load happen in this region, that is going to cause the variation in the generation in both the region. यहाँ पे भी change होगा, यहाँ पे भी change होगा, according to that variation in the load. And according to that, the new settled value of frequency will be there in both the region. Because it is a synchronous intertie, AC intertie. And asynchronous intertie, if you want to do, means both region I want to operate independently, but want to do some fixed amount of power exchange amongst them, then in that case only the HVDC interconnection has to be done. Because as ordered power is there, that we can regulate through that DC link. But if it is parallel by AC, then in that case, that control of power from one region to another region will not be there. So this is what about the parallel operation of AC transmission line. If we consider the mesh network means, as we all know, that the electrical system, which are having many transmission lines interconnected to each other at different buses, where the generators and loads are there. So here one example has been given, that there is a 3-bus system. Out of that, bus A is acting as a generator bus, bus B is acting as a generator bus, and bus C is acting as a load bus. This is acting as a load bus, where the transmission line which is interconnecting bus A to C is having a reactance 10 ohm. Transmission line which is connecting line bus A to B is having a reactance 10 ohm. Bus B to C having a reactance 5 ohm. Now for this system, let's start with the fundamentals, how this system gets operated. First of all, it is forecasted what will be the load on this particular bus during the period of operation you are looking for. What will be the forecasted load? So according to that forecasted load, let's say it is 3000 megawatt will be the load forecasted at that load bus. So according to that, we need to manage the generation. And obviously that generation we need to manage economically. That is economical generation sharing we have to do. Obviously, as the lines are modeled only by their series reactances, so there is no resistances. So because of that, the transmission lines are considered as a lossless transmission line. And as the transmission lines are lossless, so because of whatever will be the demand, that much generation we need to plan at the generating station. So there is no like generation plus losses will be the demand. Here generation is equal to the demand only, because lines is considered as lossless. So according to that economical generation scheduling, whatever will be the fuel cost curve of generator at bus A, whatever will be the fuel cost curve at generator B, and according to that fuel cost curve, it is found that lambda, that is del C1 by del Pg1 is equal to del C2 by del Pg2. That is utilized, and another equation is Pg1 plus Pg2 is equal to 3000. And from that one, it is solved for Pg1 and Pg2. And it comes that Pg1 is 2000 megawatt and Pg2 is 1000 megawatt. Now Pg1 is 2000 megawatt and Pg2, that is Pgb we can say, is 1000 megawatt. Now for this generation at bus A and B and load at bus C, what will be the power flows? So we need to find out the power flow through the lines. Now let's consider we want to find out the power flow through line PAC. So the power flow through line AC is what? Let's consider that this bus is, this generator is inactive. Superposition theorem we are using, means first only consider the one generator and load. Second, we consider the second generator and load. And then by doing the algebraic summation of that, we can find out the power flows. So PAC, power flow through line AC, when generator A is in operation. Generator at bus A is in operation. So how it will be? 2000 is the total generation. Into sharing is what? Current division rule. So whatever 2000 will be get generated. So maximum current will flow through the low impedance path. Are you understanding what I am saying? Means maximum power will flow through the low impedance path. Because we know it is inversely proportional to, power flow is inversely proportional to the reactance. So what we will do? Opposite branch reactance. हम निकाल रहे हैं ये लाइन में से फ्लो होने वाला पावर. सो अपोजिट ब्रांच रिएक्टेंस करंट डिवीजन रूल कितना है 15. सो इनटू 15 10 plus 5 15 divided by total reactance of this network is what? 25. So you will calculate it. So you will come that 25 5 3 5 5 5 4 400. So 400 into 3, that is 1200. So what happened? Out of this 200 generation, 1200 will flow through this line, and remaining 800 will flow through this line. ये लाइन से जाएगा और फिर ये लाइन से जाएगा वो 800. ये हो गया when generator at A is in operation. Now we consider generator at B is in operation. A is not in operation. Now for this, again we will find out the power flow through these lines and this line. So I will find out for this line. So 1000 is the total generation. I am considering for, this is PALA. So PAB when A is in operation is also equal to PBC when A is in operation, and this both is equal to 800 जो मैंने अभी आपको निकाल के लिखा है फिगर पे. Now for this 1000 operation, I will find out PBC when C is in, generator B is in operation, is equal to what? 1000 is the total generation into ये 1000 में से ये लाइन में से कितना फ्लो होगा? सो अपोजिट ब्रांच इम्पेडेंस कितना है? 10 plus 10 20 divided by 25. Total reactance is 25. So this is okay. 20 as it is we can say 25 ones are 1, 25 fours are 100, that is 40 into 20, that is 800. That is again 800. Am I right? So again, because of this 1000 generation, additional 800 megawatt will flow through this line, and remaining of 1000 minus 800, 200 will flow through this line. ये डायरेक्शन से फ्लो होगा ना वो 200 ये लाइन में से, because through this is the path for, and again that 200 will flow through this line. 200 will flow through this line. So out of this 1000 generation, 800 is flowing through this line, 200 is like this way, it will go to B to A and then A to C. Obviously, this path impedance is high, that's why low power is flowing through this. This path impedance is low, so that's why more power is flowing through this. So total now we will do. So this 800 plus 800, 1600 megawatt power is flowing through this line. This 800 in this direction and this 200 in opposite direction. So resultant is 600 in the larger value direction. So 600 megawatt is flowing in this direction through this line. Here 1200 in this direction, same direction 200. So 1400 megawatt power is flowing through this line. So like that way the load flow has been, this power flows through the transmission line can be estimated. Now once we found that, now we have to check. Now we have to check that the capacities of the transmission line. Let's say here it is given in the example that line AB is 1250 BC. Okay. AB is, now this line is basically having a rating of 1000 megawatt capacity. This line is of rating 1250 megawatt capacity, and this line is of rating 1500 megawatt capacity. Now here, if we look, this line is carrying 14,000 megawatt under this operating condition where the capacity is 15,000 megawatt, 1500 megawatt, so there is no problem. This line is having 1000 megawatt power handling capacity where it is carrying 1000 megawatt, so there is no problem. But if you see for this line BC, which is of capacity 1250 megawatt, but under this operating condition, the power flow will become 1600 megawatt. So what happens? This line will get overload if we operate this power system by generating the power 2000 megawatt here and 1000 megawatt here in order to fulfill the 3000 megawatt. So this line will be get overloaded. So obviously we can't operate this system in this manner. Under this operating condition, we can't operate this system in this way because that line will be get overloaded and it will get damaged. So what is the solution? So solution is to reduce the generation at one bus and increase the generation at another bus such that whatever excess power is flowing through this line will be get diverted through that underloaded transmission line. Will be get diverted through that underloaded transmission. तो उसके लिए आपको जनरेशन चेंज करना पड़ेगा. अभी आप जनरेशन चेंज करेंगे तो वो जो जनरेशन आप करेंगे, so that is not as per the economical जनरेशन शेड्यूलिंग प्रॉब्लम. और जो हमको सोल्यूशन मिला था इकोनॉमिकल जनरेशन शेड्यूलिंग प्रॉब्लम के हिसाब से, तो उसके हिसाब से नहीं होगा. सो इट मीन्स दैट वी आर नॉट गोइंग टू ऑपरेट द सिस्टम इकोनॉमिकली. सो दैट इज द what we can say where we need to manage actually. Means we are operating here system uneconomically because of transmission bottleneck. क्योंकि आपका ट्रांसमिशन नेटवर्क का जो bottleneck create है online BC. So because of that, we need to operate that transmission line, that power system uneconomically. So obviously, we have to provide the solution for this line. So solution for this line is what? You have to upgrade this line. मतलब इसका रेटिंग जो है आपको बढ़ाना पड़ेगा. Rather than designing it, आपने 1250 को डिजाइन किया था, तो आपको उसको अपग्रेड करना पड़ेगा. Some 2000 megawatt capacity that line has to be. So what you have to do? You have to go with some another parallel transmission line across bus B and C with some additional power handling capacity. Then it is possible for us to operate that given power system economically. Are you understanding whatever wording I am using here, Chirayu?
Yes, sir.
Yeah. So either you need to operate the system uneconomically or you have to go with some further action so that in future you will operate it economically. So the solution is what? You have to upgrade this transmission line such that अपग्रेड मतलब उसको हायर रेटिंग के लिए अपग्रेड करो, नहीं तो फिर उसके साथ पैरेलल में दूसरा लाइन डालो. अभी पैरेलल में दूसरा लाइन डालेंगे तो देयर इज अ इशू ऑफ राइट ऑफ वेज एंड दैट ऑल. कॉस्ट इन्वॉल्व इन दैट इज वेरी हाई. Again, it is not like we can say the time required to complete that work is also in terms of years. So till that time, again, we have to approach that system uneconomically. So what is the faster solution for that? Is there any other solution rather than going to upgrade that transmission line? Because we have a margin. This line is operating 1500 megawatt, where we are operating it 1400 megawatt. I think 1500 or 2000 megawatt it has been given. I don't know exactly. Yeah, 2000 megawatt it is given. So this line is having a rating of 2000 megawatt. ये जो है वो 2000 megawatt है, where we are operating it only for 1400. So there is a scope of diverting 600 megawatt power through this line. Again, this line is of rating 1000 megawatt, where 600 only we are transferring. So there is a scope of 400 megawatt to divert the power through this line. So how this diversion can be done? Because as we know, it is not controllable. It is not in our hand कि हम कुछ करके उसको divert कर सकते. But facts gives the solution for that. As I said earlier, the line which is getting overloaded, ये line आपका overload हो रहा है. So in order to reduce the power flow through this line, what you can do? You can add up some additional reactance in series with the transmission line so that the path of current which is coming here will be get diverted through this another path. So that is the solution given here. This is the line which is going to overload. In series with that, we can add up the additional reactance. Here they add 7 ohm reactance, which is variable they keep. Means according to operating condition, if they need to change it, so then they can be able to change it. That overall reactance of this line now controllable by means of this FACTS controller device. Here we just show the static series reactance, but it can be a power transient based voltage source or capacitor or reactor or anything else that we will see in details later. So by adding up this reactor here in this series line, what happened? For the same load, same generation going on at A bus and B bus, it is possible for us to change the power flows. And now because of this addition, you can see the power flow get limited to 1250 megawatt, here 250 megawatt, but here it is diverted to 1750 megawatt. So it is possible for us to operate the system now economically by providing the solution of additional reactors in the line which is get overloaded. Rather than this, one can say the line which is having a scope to carry the more power. ये line में हमको दिख रहा है कि 2000 का rating है, 1400 megawatt is flow हो रहा है. So we can reduce the reactance of this line. That is also the possible solution. So by providing the capacitive reactance in series with this line, we can reduce the reactance. So capacitor can be added in series with this line. So net reactance of this line we reduce so that the power flow through this can be increased, and automatically the power which was earlier flowing through this line gets little bit diverted through this line, and like in that way it is get satisfied. Third solution is rather than playing with the reactance, we can play with the phase angle. So here what they did, they reduce the phase angle difference across this transmission line. तो यहाँ पे माइनस किया है, मतलब they are basically going to reduce the phase angle difference between this, sorry, not reduce, it is going to increase because sign of delta it is ना actually. So delta का value ज़्यादा रहेगा, तभी P will be more in that line for the given fixed parameters. So here they will negative phase angle difference they add here so that the difference between this bus and this bus phase angle difference delta will increase, and accordingly the power flows we can increase through this transmission line. So you can see that when there is a bottleneck on a given power system, so the solution to them is what? Either you need to upgrade the transmission line of that bottleneck network, or you go with some flexible AC transmission devices in that network so that you can divert the power flows of the transmission lines. Means we can limit the power flow of that bottleneck line and divert that power through the another transmission lines where the margin between the actual loading and the rating of that line is available. So this is how the possible solution for that problem. Now we need to think economically and technically that whether to go with the upgradation of the line or to go with the FACTS controller devices on the line, which one is become more economical and so on. So according to that it can be done. Obviously, if by providing the FACTS solutions here we diverted it, but as in future the demand goes on increasing, so what happened, these lines
out of these two lines, one lines may get again overload. Suppose rated load pe chala gaya. So after that, there is no solution to us rather than upgradation of the lines. Rather than upgradation of the line. Means whenever there is a scope to divert the power, then and then we can use the fax control devices and divert the power and avoid that upgradation of the line for some years. So hope you understanding how the fax will help here in the given network in order to overcome that bottleneck of the network. Got it? Yes. Purvaja, are you there? Purvaja. Okay, anyway, we can stop here now. You all please mark your attendance. Please mark your attendance. Those who mark the attendance can leave the meet. Let's see how many are there actually. Those who mark the attendance can leave the meet. Shakuli, are you there? Has you marked the attendance?
Yes, sir.
Okay.